Hi. So we just finished a chapter on waves where we talked about waves in general. We talked about waves on a string. We talked about sound waves through different media, through gases, liquids, and solids. And we talked about the Doppler effect. And this chapter, chapter 17 in our textbook, is also about waves. Specifically, it's about what happens when two or more waves interact with each other and what happens there. So in general, the concepts here are wave superposition and constructive and destructive interference. All right, so let's see if I can get things going. There we go. So the first thing we're going to talk about is this idea of linear superposition. So that word superposition basically just means that when we've got two things overlapping, they add together. Specifically, we're using that to talk about waves right now, but honestly, it works kind of the same way with forces, and forces add together. And later on, we'll see that electric fields add together and magnetic fields add together. But at any rate, this chapter is about waves. So it says that when two or more waves are present simultaneously at the same place, the resultant disturbance is the sum of the disturbances from the individual waves. Okay, that's great, but really a picture's worth 1,000 words. I guess maybe 3 pictures is worth 1,000 words. So we can just take a look here at the left-hand side of our screen. There we go. And we can see what happens when we've got a wave traveling to the left and a wave traveling to the right, and they're both on the, I guess, positive side of the spring, on the same side of the spring. What happens when they meet in the middle? Well, when they meet in the middle, they are going to add together. And so we're going to get one really big disturbance. And then after that moment in time, they are going to continue along their merry ways. So we can see that this wave pulse right here has traveled to the left and now is continuing to travel to the left. And the same thing for this guy right here, that this wave was traveling to the right and now is continuing to travel to the right. They pass through each other. All right. So what happens when maybe I've got a wave pulse on the top side of a spring and the wave pulse on the bottom side of the spring, and they overlap? Well, when they overlap, they are going to perfectly cancel each other out if they are the exact same shape and we get the exact right instant of them overlapping. And that's what we see in the middle there. We see that these two dotted lines, which represent the top wave pulse and the bottom wave pulse, are adding together and just creating, a flat spring. Looks like there's no disturbance at all. But then if we let time run forward, we can see that our wave that was up here, that was up here is now continuing to travel to the left. And our wave that was right there is now continuing to travel to the right. Oops, I missed. Right there. You get the point. All right, so there are some video demonstrations that are available for this. You can see in the middle there, it says C demo and D demo. What do C and D stand for? Let's see. C and D stand for constructive, and destructive. And if I were going to label these two things, this is an example. The left-hand side of the screen is an example of constructive interference. The right-hand side of the screen is an example of destructive interference. And I'll post links to those videos in the comments, I guess, on this video. Okay. All right. So I've got a question for you now, and this one's a bit of a thinker. So we've got two wave pulses that you can see that are drawn there. They're drawn at time t equals 0 seconds. We've got one that's moving to the right and one that's moving to the left, and we can tell that with the arrows, certainly. They're both moving at the same speed. They're moving at 2 centimeters per second. And we are going to let time run. We're going to let time run for half a second. So we're going to let them move for half a second. And let's see, what does it say? It says, what will the amplitude be at x is equal to 0? So let's see, right there is our x is equal to 0 line. And we want to know what the amplitude, the combined amplitude of these two waves will be when they overlap at that specific point, half a second later. Pause the video, think about it, and when you are done, you can start the video playing again. So pause. Okay, so we're going to let time play forward half a second, and at least we're going to try to. There we go. Okay, so let's take a look, see what I'm doing. Okay, so basically I've drawn the leading side of each one of those wave pulses in blue. And then I've shifted them, how far they would move in half a second. So 2 centimeters per second. There we go, times half a second means that they would move over 1 centimeter. So that's exactly what I've done. I've moved the top guy over 1 centimeter to the right and the bottom guy over 1 centimeter to the left. And again, where am I looking? I'm interested in what's going on at this x is equal to 0 line. Okay, so let's see here. What is, what's the size of my top wave pulse at that x is equal to 0 line? It's right there. Okay, so this has a value of 1. So you see right there that along my vertical axis, that's a 1. And then my bottom wave pulse, let's see, on the x is equal to 0 line is right there. And so that has a value of -3. And again, we can see the -3 right there. So when I add those two amplitudes together, 1 plus -3 would give me -2. And that is the correct answer right there. Is choice D is the right answer. Like I said, a little bit of a thinker. Hopefully you can see it now that that we've talked through it, but it's not uncommon to be a little confused here. Okay, so that was waves on springs overlapping and adding together. We're going to go to a different kind of wave now. We're going to go to sound waves. And we're going to see the possibilities that arise when sound waves add together. The simplest example that I can think of sound waves adding together is when we've just got two sources of sound. Okay. So we can picture two speakers that are emitting the exact same tone. Maybe it's a tone of, I don't know, 500 hertz or something like that. Okay. So if these two speakers are vibrating in and out at the exact same rate, at the exact same time, and we are equidistant from both of them, meaning that, maybe we're 3 meters away from the left-hand speaker and 3 meters away from the right-hand speaker, then we will experience constructive interference at that point. And we can see this from our waves here in our figure. Let's see, we've got, whoops, let me just erase that real quick. There we go. We have constructive, excuse me, not constructive, condensations. Sorry, the C confused me. And marked, and rarefactions marked. And let's remind ourselves of what these are. Condensations are high pressure regions, and rarefactions are what? Low pressure. Okay. So we've got areas of high pressure and low pressure there. They're coming from both the left hand and the right hand speaker. Okay. And what we can see here is that, well, our left hand speaker at the point that's highlighted is, well, we're getting a condensation from that left hand speaker. We are also getting a condensation from that right hand speaker. Okay. So when I've got two areas of high pressure there, or two sources of high pressure. Those two sources of high pressure, we can picture maybe right there, high pressure there and high pressure there from our individual sources, are going to add together, and we're going to get an even higher pressure as a result. Okay, all right. So this picture that we see is frozen at one instant in time. If we let that continue to play, we'll end up, let's see, if we let it half a cycle go through, we'll end up with a low pressure region there. So maybe right here, low pressure, and what do we have? We have an even lower pressure as a result. So we can think about what goes on with our eardrums when they interact with these varying pressures. If I've got just a single source of sound, then my eardrum is going to vibrate in and out as the pressure waves, the variations in pressure, reach my eardrum. Okay. But if I've got two sources of sound and I'm equidistant from those two sources of sound and they're playing the exact same sound, the vibrations are going to be even greater. So my eardrums are going to be vibrating even greater, and I will end up hearing a louder sound as a result. So these two add together. All right, so let's see what happens if maybe I'm not equidistant from my two sources of sound. So here we can see that I'm 3.5 meters away from the left-hand speaker and 3 meters away from the right-hand speaker. Incidentally, it looks like these figures are drawn so that the wavelength of the sound is exactly 1 meter. So that might help us to think about it a little bit. All right, so for the specific instance that I have drawn right there, I can see that what do I have from the left-hand speaker? I've got a rarefaction. I've got an area of low pressure. And then for my right-hand speaker, I've got an area of high pressure. Oops, high pressure, which would be a condensation, not a rarefaction. So this would be a condensation. Okay. So I've got an area of high pressure and an area of low pressure adding together. And if I've got high and low adding together, and they're the exact same frequency, then they are going to cancel out. And so what I've got drawn over here is a summation of those two waves. And what do we see? We see just a flat line. Let's think about the ramifications of this. So basically what I've told you here is that I could have two speakers playing the same frequency, and even playing it loudly. And if I'm in the right spot in a room and maybe I plug up one ear, that I could actually find some place where I wouldn't hear any sound at all. That seems a little shocking. It turns out it's true. It's true. It's a little hard to actually do this, and there's a reason for that. We've got kind of a simplified model here, two sound sources. If we put those two sound sources inside of a room, then the sound is going to bounce off the walls. So we could definitely get to places where if we block our ear and move around, that we will hear a much dimmer sound than in some other places. But it's kind of hard if we're trapped inside a room to hear no sound at all. This is an experiment that I have done in the classroom. It's an experiment that, unfortunately, due to our interaction right now, me being in a video and you sitting there, that we just can't really do it, which is too bad. But yeah, you'll, I guess, maybe have to take my word for it, or I'll give me a second and we'll see what a resource that maybe you'll be able to use. All right, so this idea that we could actually have two sources of sound cancel each other out is exactly what goes on in noise canceling headphones. And this is kind of cool. It's a neat little application here. We've got a source of sound coming in and into, from the outside world. Maybe it's construction, I don't know. And we would like to get rid of the construction. So what happens is inside these noise canceling headphones is that a microphone picks up that noise. And then we go through some electronic circuitry to invert the signal. And then a speaker there plays an exact inversion of that outside noise. And so as a result, we've got two sources of sound here. We've got sound coming from the speaker, and then we've got sound coming from the outside. And then you hopefully can see that when we add these two together, we actually end up mostly canceling out the sound. We probably can't quite get perfect, but it's really kind of cool that we can have two sound sources and they cancel each other out. So what's going on there? One sound source may be producing a high pressure, spike, maybe right there. And the other sound source is producing a low pressure spike right there. And so when these two add together, the high pressure and low pressure cancel out, we get, our pressure just right at our median level, which doesn't excite our eardrum. Cool. All right. Okay. There is a lot here, and unfortunately, there's not a real good way for me to break up this video into multiple pieces. So we're going to suffer through it. On the previous slides, I provided examples of constructive and destructive interference from two sound sources. And this slide tries to help us to be able to quantify that, to actually figure out where those points would be. Where those locations would be, where I would have constructive interference and destructive interference. If, say, I've got two sound sources and I'm a certain distance away from each one of them, what is it that governs whether I will hear a loud noise or no noise at all? Okay. So here's what we're going to do. We're going to take a look at some of these spots that are drawn. We've got red spots drawn and we've got white spots drawn. Okay. And we've got waves coming from our speakers. So for the sake of our discussion, let's say that the wavelength here is 1 meter. That's going to allow me to talk about this a little bit better than just saying wave. Okay, so let's look at maybe this dot right here. It's the one that we kind of looked at already, but I think it'll help to start with that one. So what we can see here, if we start counting how far away, how many wavelengths we are away from our left-hand speaker, it looks like we are 1, 2, 3 wavelengths away. So let's see, 1, 2, 3 wavelengths away. And then if we start counting from our right-hand speaker, we are 1, 2, 3 wavelengths away. Okay. So what I can do now is I can calculate the difference in distances. That difference in distances, we can represent this with delta PL and call it a difference in path lengths. But it's a difference in distances from my two sources. So this would be what? My path length from my left-hand source minus my path length from my right-hand source. So in this case, given that I've got a lambda there of 1 meter, and I've got my waves nicely drawn out, this would be 3 meters minus 3 meters would give me 0. Okay, 0. If I look at my condition for constructive interference here, I see that if my path length difference, in this case is 0, is equal to what? N times lambda, where n is 0, 1, 2, so on and so forth, then I will have constructive interference. All right. This is the first example of that. I told you this is a little bit dense here, so bear with me. Let's look at another spot. Pin. Okay. Let's look at another spot. Let's look at maybe this spot. Whoops. I lied. I played a trick on myself. Trick on you. Let's look at maybe this spot right here. So that spot right there, if I'm coming from my left hand speaker, I am 1, 2 meters. Because I said that we were going to mock up and use the idea that our wavelength is 1 meter. I'm just making up a number. So my path length from my left-hand speaker this time is 2 meters. What about from my right-hand speaker? 1, 2, 3. My path length from my right-hand speaker is 3 meters. My difference in path lengths is going to be the difference in those two numbers. And I want to do bigger minus smaller so that I end up with a positive value. This is going to be 1 meter. Okay, so my difference in path lengths is 1 meter. And my wavelength is 1 meter. All right, so I can look at these two conditions here and try to see which one of them this matches up with. So if I've got a path length of 1 meter, and let's see, I've got a wavelength of 1 meter, what I can do is I can try to figure out, well, what multiplier is it that I would get that would make this equation true? So delta PL is equal to X lambda. I could picture it like this. Delta PL is equal to X lambda. And I've stuck in 1 meter for my delta PL. I've stuck in 1 meter for my lambda, and I can figure out what X is right away here. X is going to be equal to 1. Okay. Well, if X is equal to 1, that means that, well, that satisfies my condition for constructive interference. If that multiplier there on lambda, right there, is an integer, is 0, 1, 2, 3, so on and so forth, that means I've got a constructive interference spot. All right, let's take a look at one of the white dots now. Okay. So one of the white dots. So let's maybe focus in on this one right here. Left-hand speaker, right-hand speaker. Okay. And still using the idea that my wavelength is equal to 1 meter. If I look at the distance here away from my left-hand speaker, I am 1, 2.5 meters away from my left-hand speaker. Okay. So my delta P, or excuse me, not my delta PL. Let me fix that real quick. My path length from my left-hand speaker is equal to 2.5 meters. Okay. Again, using just this mocked up value of lambda is equal to 1 meter. Let's see, let's look at my path length away from my right-hand speaker. I am 1, 2, 3 meters away from my right-hand speaker. So my path length from my right-hand speaker is equal to 3 meters. If I find the difference between those two, my difference between those two is going to be 3 meters minus 2.5 meters is going to be 0.5 meters. 0.5 meters. Oops, okay. All right, so that's my path length difference. Let's use this idea that delta PL is equal to X times lambda and figure out what X is for this specific example. So need to make a little bit of space here. Use my finger, that's faster. I'm trying to use the cursor, it's no good. Okay. All right, so delta PL is equal to X times lambda. We figured out that our delta PL in this case was 0.5 meters. And that's equal to X times lambda. Lambda is 1 meter. So if I divide 0.5 by 1, I can see that, and let's erase that little blurb real quick. I can see that x is going to be equal to, darn it, so frustrating, x equals 1/2. 0.5 divided by 1 is 0.5. That's 1/2. All right, so that's the multiplier on my lambda in this case. So which one of these does this match up for? Is it constructive or destructive interference that would occur? So if I look at my possibilities for destructive interference, I can see that, sticking in the different values that I have for in there, if my delta PL is equal to, let's see, 1/2 lambda, or 3/2 lambda, or 5/2 lambda, or so on and so forth, I'm going to have destructive interference. So in this case, my delta PL is equal to what? Is equal to 1/2 lambda. So as a result, I've got destructive interference for this white spot that we've analyzed. Okay. All right. So I can see that with the math that I've got, my condition for constructive and destructive interference that I've got on the screen. The other way that I can see that is, well, if I clear this off real quick, there we go. If I clear that off, I've got a rarefaction there from my left-hand speaker, and I've got a condensation here from my right-hand speaker. And when I add a rarefaction and a condensation, I get, well, just no pressure at all, or no variation from atmospheric pressure at all is what I should say. All right. There are a couple of resources that I've got on this slide. There are videos that I'm not actually going to post a link to, but there's also this online tone generator right here. So you can go to onlinetonegenerator.com, which this is not a link, but you can type that into a web browser. And that will play, well, if you hit the play button, I think it's set to 440 hertz. You can mess around with the frequency for that. You can plug up one ear, so that we only have one place that we're listening to the sound at. Look, here we've got two places, now just one place mostly. And then you may be able to bob your head around or get up and move around the room as this sound is playing from your computer. Obviously, don't use earphones when you're doing this. Listen to the sound coming from your laptop speaker or whatever. Move around the room, and it really doesn't take a whole lot of motion at all, probably just as much as I'm moving my head right now, to find areas of where you hear a lot, a loud noise, or a much dimmer noise. So this actually does check. All right, so what do we have here? Well, we've got everything I just went through. We've got our problem-solving technique for how to handle if we want to figure out whether a specific location has constructive interference, destructive interference, or it could actually be something in between. It's only these very specific spots where we have purely constructive or purely destructive interference. So we figure out the distance from our two sources. We take the difference in those distances. If we know the wavelength of the sound, we can figure out what X is. And then if X is an integer, we've got constructive interference. If X is a half integer, something like 1/2, 3/2, 5/2, that would be 0.5, 1.5, 2.5, 3.5, then we would have destructive interference. All right. Let's do an example problem real quick. Okay, so this says, for the person that's this distance away from the two drawn speakers there, does this person hear a loud sound or no sound? So we're given the geometry. and we're given the frequency that's playing from these two speakers. We're given the speed of sound. So from this information that you're provided, does the listener hear a loud sound or no sound at all? All right. We've got speaker A and speaker B. So one thing that we can see right away is that our path length from speaker A is 2.4 meters. We would like to know our path length, sorry, my bad. Our path length from speaker B is 2.4 meters. We would like to know our path length from speaker A. So that's this guy right here. Okay. Well, we can figure that out real quick because we've just drawn the leg of the hypotenuse of a triangle, and we've got the two side lengths, 3.2 meters and 2.4 meters. And we definitely see that it's a right angle. So we can use what? We can use Pythagoras here, the Pythagorean theorem, to figure out our path length for A. So our path length for A is going to be equal to the root of 3.2 squared plus 2.4 squared, Pythagorean theorem. This is going to give us 4.0 meters. Our difference in our path lengths, then our difference in our distances from the two speakers to the person would be putting subscripts on things where they don't belong. Our difference in our path lengths would be 4 meters minus 2.4 meters would be equal to 1.6 meters. Okay, so that's our difference in path lengths. We remember the equation that we've been using. It says that difference in path lengths is equal to x times lambda, and we want to figure out what that x is. And we know that if that x is an integer, we've got constructive interference. If that x is a half integer, I guess I should be saying half an odd integer, then we've got destructive interference. So great, we've got the delta PL. Let's see, if we knew what our lambda was, then we could proceed on and figure out what x is. But we could figure out that lambda real quick because we know that speed is equal to wavelength times frequency for any wave. So if I stick in my speed of 343 and my frequency of 214, 343 over 214, I will be able to figure out that my wavelength here is 1.6 meters. Okay. So now I can change that question mark from a question mark to a check because I know what that is now. So let's see, x here is going to be equal to my difference in path lengths divided by lambda. This is 1.6 meters divided by 1.6 meters is 1. Oh, x is 1. Okay. So then I think about the condition for constructive interference. Let's see here. There we go. Okay. If the thing that's multiplying my lambda is an integer, then it's constructive interference. Cool. So that means that I've got constructive interference in this case. And so in terms of the actual question that's asked on the screen, that means that I hear a loud noise. If I had gotten x is equal to 1/2 or I don't know, maybe 1.5 or 2.5 or something like that, then I would have had destructive interference instead. But clearly that's not what happened. In this case, we had we had our x is equal to 1, so we have constructive interference. All right. That does it for this. There's another brief example that I'll provide, but that's going to pop up in another video.